Good morning, everyone. This is Philip Griffiths, and I'd like to welcome you to the last workshop of the year on Hodge theory that's being held at EMSA. Our first speaker this morning is the first of two talks on the subject. It will be by Jun He on Kazhdan-Lusztig theory and singular Hodge theory of Matroids 1. Jun, the floor is yours.
Okay, thank you for the introduction and thanks for joining me today. I am very, very happy to be with you in this our virtual space, and I hope your year has been going fine. So I'm going to tell you about my joint work with Tom Braden, Jacob Mathern, Bo-Tong Wang, and Nick Proudfoot. And we have been working on this project for quite a few years. And we found an algebraic and combinatorial structure that we find quite remarkable. So I would like to share the story behind these structures. So this will be the first part of two talks. So today, I'm going to tell you a little bit about the combinatorics, or more precisely, the problems in combinatorics that led us to think about these structures. And tomorrow, I'm going to tell you about the algebra that lets us to solve these combinatorial problems and the geometry that motivated us to consider these algebras. So the very first problem that gave us the hint to the existence of these structures that's closely related to what we are now calling Kazhdan-Lusztig theory for matroids is the following theorem of de Bruijn and Erdős from the 40s. It's a theorem from a paper, one very early paper of theirs with a terribly generic title on a combinatorial problem. And if you look at that paper, there is one theorem in it, and it's a very simple theorem asserting a numerical inequality between two quantities. And the statement goes like this. So it's a statement on a finite set of points on a projective plane. And it says that every set of points, say E in a projective plane, determines at least cardinality of E many lines, except in one case where the entire set E is contained in a single line. So let me elaborate on what we mean by determines. So here determines simply means to connect every pair of points by a line and see how many lines do we get. So for example, in the first picture here, which is the picture of 4 general points in a plane, what we get is 1 line, 2 line, 3 line, 4, 5, and 6 lines. So in total, we get 4 points determining 6 lines. And de Bruijn and Erdős is telling us that 4 is a lower bound of 6. So this is perhaps the simplest case of the assertion, but of course there are more delicate cases, and the simplest non-trivial case next to the generic case would be 4 points in a non-generic position, where 3 of the points are in a single line. Then we see that there are 4 lines that are determined by these 4 points. So in this case, actually, the inequality asserted by de Bruijn and Erdős is an equality. Okay, so now let's consider the more interesting case. And this was actually one of the examples that led us to the geometry construction. So this is the famous configuration of 7 points in a projective plane over a field, where we take all the 7 points with 0, 1 coordinates, except of course 0, 0, 0. So in this case, if we connect all the pairs of points by a line, then we get 1, 2, 3, 4, 5, 6, and then 7, 8, and 9. So we get the inequality that 7 is smaller than 9. What is interesting about this configuration is that you can think of the same configuration over different fields. And if you consider the same configuration of 7, 0, 1 vectors over a field of characteristic 2, then you get actually different numerics. You get 1, 2, 3, 4, 5, 6, and 7. So here you see the second case of equality between the number of points and the number of lines. In fact, Ruin and Erdős characterize the case of equality as well. They characterize it either your configuration of points must be a pencil, as in the 4 equals 4 case, or the full projective plane, as you see in the 7 equals 7 case. But one of the things that is interesting about this statement is its generality. So what do we mean, or what do they mean by a projective plane in their statement? So as algebraic geometers, we typically think of projective planes defined over some field, but their projective plane is a completely general one, the one defined by combinatorial incidence conditions. So in particular, your projective plane need not be defined over any field, yet their combinatorial reasoning is just as valid, and the numerical pattern works in the same way. So people thought about the argument and tried to generalize or find similar patterns in higher dimensional cases, still while preserving this abstract incidence geometric nature of the statement. So one of the natural extension of their theorem can be phrased using the language of Matroids, which was introduced by Whitney in the 30s. So one of the marvelous things about Matroids is that it can be defined in several different looking but equivalent ways. So Whitney defined the Matroids in one way and showed that it's equivalent to the others. And subsequently, there were works of Birkhoff in the sense of lattice theory and McLean in the study of transcendental independence of rational functions, and many, many others, which all were subsumed into a single study of Matroids. And let me just show you 2 of the possible definitions, which all turn out to be equivalent. So one of the definitions, in terms of basis of a matroid, will play an important role in the geometry that I'm going to show you tomorrow. And the second definition I'm going to show you is in terms of flats, which will control the structure of the algebra that I'm going to briefly show you today. So in terms of the basis, you can say that a matroid on E, where E is just any finite set. So now we are entering the realm of abstract combinatorics that has nothing to do with fields or anything. A matroid is simply a collection of subsets that you call bases that satisfies the exchange axiom, which says that if you have 2 bases, say B1 and B2, And any element I1 in the first space is B1, not in the second base is B2. Then the axiom is that there is an element I2 in the second base is B2, not in the first base is B1, such that if you interchange I1 and I2 with respect to B1 and B2, then you can make the new pair of subsets both bases. So this may remind you of the famous Steinitz exchange axiom that you learned in linear algebra. Or more recently, this axiom has been recognized in tropical geometry as the tropicalization of the Plucker relations that hold between maximal minors of a matrix. So it says that if you write down a Plucker relation between the minors, it says that if you have one non-zero term in your expression, which sums to 0, then you must have some other non-zero term, which turns out to be exactly this, if you know how the Plucker relations look like. So every term is a product of pairs of bases. And if you write down this very basic principle of algebra, it turns out to be exactly the basis exchange axiom. So that is one characterization of matroids. So in terms of point configuration, say in the projective plane, which was the case of Dubreuil and Erdős, this collection of subsets B is the collection of all subsets of 3 points in the plane that are in general position. So this is what you would call a basis in that case. Any questions so far?
So maybe I have a question.
Yes.
So you studied this kind of arrangement on the projective space, and studies if abstract line arrangement can be realized as
Yes.
a line arrangement over R over C, right? And I remember that.
Yeah. Yes.
Yes, sometimes a certain arrangement can be realized in over finite field, but not over complex number, right?
That's right.
And I remember that Friedrich Hitzbuch many times ago studied already this type problem. The idea is very simple, right? Maybe certainly you know that. He constructs certain Kuma cover of the space ramified along the given arrangement. Then look at the solved singularity, look at the Miyaoka-Yau inequality. You get certain control on the data for this line arrangement. So what's the relation between his method and the method of Hitzbuch and your method?
So if I recall correctly, Hitzbuch's method or construction was very specific to like surfaces, two-dimensional cases.
A high dimension, I believe it can also work. I mean, this kind of Kuma construction can be done for any variety given arrangement of divisors, right? You can do this kind of thing. But the simplest case is just a two-dimension case.
Yes.
But I think what Hitzbuch used is also quite a very strong method from the no-linear partial differential equation, so-called K-line symmetry, due to Yau. He really solved some problem. Certain arrangement can realize over F2, but not over complex number. This is very surprise. But
you're seeing one example right here.
Yeah, something like this. Yeah, I cannot remember exactly the data, but I certainly know this kind of things.
Yeah.
Yes. Okay.
So one thing that was somewhat surprising in constructing the objects that I'm going to introduce was their generality. So they are blind to the characteristic of the field, even the existence of the field that would represent these abstract configurations. So for example, if you apply our construction to point configuration that only lives over a field of characteristic 2, you will get a variety defined over a field of characteristic 2, which has its L-adic cohomology and L-adic intersection cohomology and so on. But our construction gives you a model that is defined with Q coefficients. So it allows you to study finer properties of these resulting algebras or modules that are reflected in the fact that you are now dealing with algebras over Q rather than algebras over QL, for example. So I'll show you some of the delicate things that can appear when moving back and forth between different fields.
Thank you.
So this is the basis characterization. And another characterization that I'll more intensively use of matroid is the characterization in terms of flats. In this axiomatization, you would say a matroid on E is a collection of subsets L. So L is a collection of subsets of finite set E that satisfies the flat partition axioms. So exact nature of these axioms will not concern too much for us for this hour, but I'm just showing you what they look like. So the first property that you want is that if F1 and F2 are flats, then their intersection is a flat. And the second one, which is the main property that you want to require in this axiomatic incidence geometry, is that if F is a flat, then any element not in F is in exactly one flat that is minimal among the flats strictly containing F. So that was a lot of words, but it means that any element, say a point, not in a subspace is contained in exactly one subspace that covers the given subspace in the poset of all subspaces. So this minimality is relevant here. So the basis is, I think, self-explanatory. The flat here, you should think of the subspaces, either in vector space linear algebra setting or in the projective geometry setting. And one of the surprising fact is that these two seemingly very different axiomatizations lead to the same class of structures, which is the structure that we call matroids. So roughly speaking, if you know all the bases of M, then you know all the independent subsets of M defined as subsets of bases. And then you know the rank function that assigns a number to arbitrary subsets of E, defined as the maximum size of independent subsets contained in the given subset. And if you know the rank function, then you know what flats are. Flats should be the maximal subsets of given rank. So this is the span of certain finite collection of subsets. And it should be a fun exercise to go from L to B as well. So there is a bijection between the collection B satisfying the exchange axiom and the collection L satisfying the flat partition axiom. So here are two classes of famous examples of matroids, which were the motivating classes of examples. So one is coming from graphs, the other is coming from vector configuration. So for example, my finite set E, the ground set, can be the set of edges of a given graph G. And if you set script B to be the collection of all spanning trees of G, then you can check that the basis exchange axiom holds for this collection, and therefore it defines a matroid. So if I have a cycle with 4 edges, I have 4 bases, each consisting of 3 edges of the given 4 cycle. So these are called the graphic matroids. And in some precise sense, you can argue that these generalizes the class of graphs. The second example is when you take your E, the ground set, to be a finite set of vectors in a vector space over some field F. So this F is my field. It could be anything. It can be really a division ring or a skew field. And here, basis is what you think they are. The basis in the sense of linear algebra. But the flats are given by the collection of all subspaces spanned by subsets of E. So this is exactly what de Bruijn and Erdős were doing. So points, if you think of them as vectors, joining them by a line is look at the span of the collection of such vectors. So for example, if you have 4 general vectors in 3 space, then the lattice of flats of L, this is a certain finite poset, you can represent them by associating to each subspace the collection of vectors contained in that subspace. So I have a 0-dimensional subspace spanned by the empty subset of E, and I have a 4 one-dimensional spaces spanned by each one of these 4 vectors, and I have a 6 two-dimensional spaces spanned by a pair of vectors, and I have exactly 1 3-dimensional vector space spanned by any subset of the 3 vectors. So that is my poset of all flats of L. So I'm going to refer to it as the lattice of flats rather than a poset of flats, because it's a very special type of poset called the lattice, because it's closed under the intersection. And you see that, in fact, the first example I have shown you here in terms of the 4-cycle graph, and here in terms of 4 general vectors are the same matroid. Both of them have exactly 4 bases, 1, 2, 3, 1, 2, 4, and so on. And they also have exactly the same set of flats. So whenever you have a matroid that arises in this way as a vector configuration over a field F, you say that these matroids are representable over F. Some matroids, as was pointed out before, representable over some specific field, not representable over some other field. Some matroids are representable over all fields. But one of the things that was recently discovered by Peter Nelson is that almost all matroids, in a precise sense, in an asymptotic sense, are not representable over any field. So simply there are a huge number of matroids on a given ground set E when the ground set of E has sufficiently big, many number of elements. Okay, so this is the combinatorial structure that I wish to investigate. But if this is too much axiomatization to carry around for you, it is enough to, for now, just to think of a vector configuration in a vector space. Maybe over characteristic 2 or over some other thing over Q. It doesn't really matter for this time. So let's think of vector configuration or a graph from now on. So in terms of matroids, Dowling and Wilson in the 70s proposed the following generalization of de Bruijn-Erdős theorem for point configuration in the plane. So now let's fix any matroid, and let's write D for the rank of the matroid. So in terms of a basis, this is the cardinality of any one of the bases, and all the bases have the same cardinality. Or in terms of the lattice of flats, this is height of the lattice of flats. And let's write our L, the lattice of flats, which is a graded lattice, as a disjoint union of its rank level sets, L of a K. So L upper K is by definition the collection of all rank K flats. So if I have a vector configuration, and if I'm looking at all the subspaces spanned by subsets of the vectors, then I'm looking at K-dimensional subspaces. There are finitely many of them. And the conjecture that generalizes the previous observation is that for any K, which is at most D half, the number of K-dimensional subspaces that are spanned by the vectors must be bounded above by the number of co-dimension K subspaces spanned by the subset of the chosen set of vectors. So De Bruijn and Erdős case is when D equals 3. So if you projectivize, you get P2 and K equals 1. So the assertion there was that L1 has size bounded above by L2. So points and lines in P2. But the conjecture is that something like that should hold in general. So comparing K-dimensional subspaces with co-dimension K subspaces. In fact, they conjectured more, something slightly more structural. So in fact, they predicted that there is an injective map from the set of rank K flats to co-rank K flats. So the existence of injective map between these two finite sets is exactly equivalent to the asserted numerical inequality. But the added assertion here is that this is not just any injective map, but a matching, the one that preserves the incidence relations. So this injective map I is required to have the property that any flat F is contained in the image I of F for every flat F. So if you think of a point and line incidence as a bipartite graph, then this is exactly the matching in the sense of graph theory. So injective map from points to lines. So the special case of this has been verified. Of course, as we have mentioned, De Bruijn and Erdős is the case of D equals 3 and K equals 1. And later, Motzkin and Curtis Green showed the statement for D arbitrary and K equals 1. So Motzkin proved the numerical inequality comparing the number of vectors and the number of hyperplanes. And then Green generalized that assertion to show the structural part, the existence of matching between points and hyperplanes. So what we can do.
Excuse me, I have a question. So
yes.
Surely duality must play a role here, where, say, in the projective case, you swap points and hyperplanes. So how does this conjecture relate to duality?
So in fact, what is very interesting in this conjecture is the failure of duality. And this is what led us to think of intersection cohomology. So here, L, I have referred to them as the collection of K-dimensional subspaces. But if you go back, it's not all the subspaces. This collection is determined by the matroid data, which is the chosen set of vectors. So I'm fixing a finite set of vectors in a vector space over F. And I'm only looking at subspaces spanned by subsets of E. So for example, if I have 4 general vectors, then it spans 4 one-dimensional spaces and 6 two-dimensional spaces, and 1 three-dimensional space and 1 zero-dimensional space. This is exactly the game we are playing with De Bruijn and Erdős in the projectivized picture, joining pair of points by a line. So what is interesting here is that I started with 4 points, but ended up with 6 lines in the P2. So the number of points and the number of lines spanned by the points are not equal in this case. Does that answer the question?
Yeah, it'll sort of do for the time being.
Yes.
I'll think some more.
Okay. Yeah. So in the later we're going to see this inequality between the two numbers as the failure of the Poincare duality pairing of a certain algebra that we're going to construct from a matroid. And it turns out that you can also construct what would be the intersection cohomology of a certain variety, provided that such a variety exists, which need not be the case. And then you can deduce the conjecture from the what you would call the Hart-Lefschetz property for such an algebra. So now we can prove that this conjecture holds in general in arbitrary rank for arbitrary matroids. And one of the interesting part is that the proof is closely related to what you would call the Kazhdan-Lusztig theory, not for reflection groups or Weil groups or Coxeter groups, anything like that, but for matroids. So I'm alluding to the existence of a structure that is structurally very closely related, or not related, parallel to the existing and well-known theory of Kazhdan-Lusztig concerning Coxeter groups. Okay. Any other questions at this point? So let me try to show you one other simple combinatorial example that gave us the idea. And this is the famous Sperner's theorem from the 20s. And it says that if E is a set of cardinality D, so any set with D elements, then the maximal number of pairwise incomparable subsets of E is D choose D half. So this is a statement of the well-known theorem bounding the size of the maximal anti-chain. So this is the number of pairwise incomparable subsets of E. And you see the obvious choice for the pairwise incomparable subsets of E achieving the bound, namely the collection of all subsets of size D half. And there are several different ways of proving this classical statement, but one of the proofs goes like this, and this is also very well known, where you set L to be the poset of all subsets. And then what you show is that L is the union of exactly that many chains in E. So here chain is a totally comparable collection of subsets. So for example, in D equals 4 case, what you show is that you look at all the subsets of the given set E. So E has 4 elements in this case, and what you show is to partition this pose set into disjoint union of chains. So I have a 1 chain here, and I have a 2 going to 2, 3, going to 2, 3, 4. That's another chain. I can start from 3, go to 1, 3, and 1, 3, 4. That's another chain. I can go 4 to 1, 4, and 1 to 4. That's another chain. I have a single element chain 2, 4, and single element chain 3, 4. And there are several ways of showing the existence of such a decomposition, but the observation is that once you have shown the existence of the decomposition into chains, then you have the bound on the number of pairwise comparable subsets. Because no matter which collection of pairwise comparable subsets you have, every one of the subsets in your collection must intersect a chain at most once. So bound on the size of one also gives the bound on the size of the other. And there is a well-known way of, or analogy, relating this picture to the picture that we often see in the Lefschetz decomposition. So I have a pose set with 1 element, 4 elements, 6 elements, 4 elements, and 1 elements. And what we typically do, as usual, is to look at the picture given by the Lefschetz decomposition. So if I only look at the primitive parts, I have a one-dimensional part generating a chain in an algebraic sense of length 5, and I have a 3 primitive parts that appears in the next degree, each of which generates a chain of length 3. And then lastly, in the middle, I have a 2 extra primitive parts that corresponds to these 2. And in fact, the Q-deformed version of the same statement holds in the sense that whenever you start with a finite vector space and you look at the pose set of all subspaces, which gives you a finite pose set, then you have the analog of the Sperner's theorem, replacing all the numbers by their Q analogs. And the typical way of proving that statement is to prove the Hart-Lefschetz property for a certain algebra that we'll get as a special case of the general construction later. Okay, so let me give you the definition of the Kazhdan-Lusztig polynomial. So typically, such a polynomial is associated to a pair of Weil group element or Coxeter group element, and they have played an important role in geometric representation theory, and they have well-known connections to the theory of intersection cohomology and so on, perverse sheaves. But now we're going to introduce a very similar looking definition for a matroid. So I'm going to define one polynomial with one variable q for every one of the matroid that I'm going to think of as the lattice of flats. So L here is the matroid of rank D. And you are going to see some similarities, but also differences compared to the original case of Kazhdan-Lusztig. One of the biggest differences is that I'm defining one polynomial for every matroid. if you go back to the Weil group setting, what you're doing is that you're defining one polynomial for every pair of elements in your poset, which is the Brouillard order in that case. So what is the difference? So really the scope of the theory is exactly the same, but here we get the simplified picture because for matroids, we have the following constructions. So L upper F and L lower F are supposed to be the intervals from the minimum element and the maximum element inside L. So these are intervals in my poset L. And what is different from the Brouillard order case is that now each of these are matroids on their own right, which is not the case for the Brouillard order. So we get the simplified picture, but not too much simpler. So if you think of in terms of the vector configuration, upper intervals and lower intervals from a F corresponds to restricting your vectors to F and projecting away from the flat F to get the new vector configuration in a smaller dimensional vector space. So intersection and projection. So these are defined by, well, they can be defined by many different ways, but the combinatorial way that is most similar to the known combinatorial way for the classical Kazhdan-Lusztig theory goes as follows. So it's an inductive definition. And the first property that you want is that PLQ is 1 if the rank of your matroid is 0. So this is a trivial matroid of rank 0. There is exactly 1 for every ground set. And the second property that you want looks very similar to the degree bound that you see in the Kazhdan-Lusztig theory, which says the degree of my polynomial is strictly less than d half. If d is positive, and 3, and this is the main requirement, this is the symmetry relation, which says that q to the d, p to the l, q inverse. So this is the polynomial that you obtain by reading of the coefficients backwards, in a sense. And that should be equal to the sum over all flats of some other polynomial chi that I'm going to tell you soon, LF of a Q and P of a LF of a Q. So L upper F and L lower F. Here, this chi polynomial is called the chromatic polynomial or the characteristic polynomial because it is exactly the chromatic polynomial counting the number of vertex colorings in the case when your matroid is a graphic matroid. So one thing that you wish to note in this proposed recursive definition is that it is not obvious that this is well defined. So among other things, there are several issues on this, but the exact same issues that you will see on the classical Kazhdan-Lusztig theory is that you see the same quantity P of a L that you are trying to define in a recursive way, probably inductive on the rank, on the other side as well. Because one of the summons that you're considering here will be the minimum of your poset, in which case you are seeing the PL of a Q as one of the summons that you are now trying to define. But if you consider the degree requirement, that degree of a PL is strictly less than d half, that was imposed in the second case, you see that the PL that appears on the right-hand side and the PL that appears on the left-hand side have disjoint support in the sense of polynomials. So on one side, you have a polynomial, all of whose terms have degree larger than d half. And on the other PL, you see terms of degree smaller than d half. So this equality imposed here looks overdetermined. But some sequence of minor combinatorial miracles shows you that this is actually a well-defined definition. And it is natural to suspect the connection to the Dowling-Wilson top-heavy conjecture introduced before, because you can compute at least one coefficient, non-trivial coefficient, in a combinatorial way. The other coefficient, you can also write it as a complicated alternating sum, somewhat like in the classical Kazhdan-Lusztig theory. But this one, the linear term, its coefficient turned out to be the number of co-rank 1 flats minus the number of rank 1 flats. And the conjecture posed by Ben-Elias and Nicholas Proudfoot and Max Wakefield in 2016 was that all coefficients of PLQ are non-negative. So this is the analog of the big conjecture by Kazhdan and Lusztig, saying that the Kazhdan-Lusztig polynomials in the classical setting have all non-negative coefficients, which was recently settled by Ben-Elias and Jordi Williamson's work on abstract Hodge theory for Sorrel bimodules. And the proof of this statement is philosophically similar, although the technical details differ in interesting ways. One of the things that is most significantly different from their setting and in our setting is that these matroids admit a very wide variety of automorphism groups. So in fact, it's known that any finite group can appear as the automorphism group of some matroid, analogously to the well-known statement for graphs. You can define the whole Kazhdan-Lusztig theory equivariant with respect to that finite group. So if finite group W acts on my poset L, and there are several interesting examples, then you can define the equivariant Kazhdan-Lusztig polynomial basically in the same way. So I'm just showing you the expression that uses the induced representation along an isotropy subgroup, fixing a flat F. And if you replace the condition 3 here by their equivariant generalization, you get equivariant polynomials whose coefficients are classes, isomorphism classes of linear combinations of representations of the given finite group W. And the conjecture here is that all coefficients are non-negative, meaning that these alternating linear combinations of recursively defined representations of W are in fact actual representations of W. So this is interesting because many of the sporadic groups naturally are defined as automorphism groups of some well-known matroids, like the Steiner triple system 5824, acted on by M24. So for example, whenever you have such a setting, we are saying that the Kazhdan-Lusztig theory naturally produces a sequence of representations of M24 that are natural in some mysterious way. And we don't know what they actually are, but they are defined in recursive way. And if you look at which one of the representations that you appear on the right-hand side, they are also all very interesting. So they are the groups that appear as the upper and lower intervals, and these are all coming from, for example, the smaller Matthew groups and so on. So these representations somehow fit together in some miraculous way, and they produce a sequence of representations. So the theorem in this setting, also by the same set of authors, is that this conjecture holds as well. And the proof of this is very closely related to the top-heavy phenomenon that we have observed for vector space configurations. So the real theorem that implies both of the asserted numerical inequalities, one on the number of flats of a matroid and the other on the coefficients of the Kazhdan-Lusztig polynomials of matroids, is the existence of a certain algebraic structure. So this is a certain module over a very simple ring. This is the so-called the graded Möbius algebra. Of L, which we are going to write as H of L, and pretend that it's some sort of a cohomology. And it is simply the sum of HK of L's, okay, from 0 to D. D is the rank, where HK of L is simply a vector space based on the formal sum of flats of rank K. So I'm just turning my vector space, I'm just turning my poset of flats into a vector space with the multiplication defined by a join in the sense of lattices. So if the rank of the join is the rank sum of the ranks, and 0 if otherwise. So it's some very simple graded algebra, and the theorem that I'm going to make precise next time, that implies all the previous statement, is that there is a graded HL module, IHL, with non-degenerate pairing between complementary degrees of spaces, graded pieces, and these are all defined over Q coefficients that satisfies the Hard-Lefschetz property and the Hodge-Riemann relations. In addition, H of L arise as a submodule of IH of L. This statement alone, without knowing anything about IH of L, implies the top-heavy conjecture. Because this H of L, just by looking at the way it's defined, the dimension of the degree K part is exactly the number of rank K flats. So if you have some module that satisfies the Hart-Lefschetz property. So an isomorphism between degree k part and co-degree k part, which contains h of a k, whose dimension is what we are trying to understand, as a submodule. Then you notice that although isomorphisms do not restrict to isomorphisms onto subobjects, injective maps restrict to injective maps. So you get the injectivity from hk to hd minus k, therefore proving the inequality between their dimensions, which are exactly the number of rank k flats and rank d minus k flats, starting from a given configuration. But of course, there are more things to say on exactly what this IH is. And some parts of this question we are still thinking of it. And the connections to geometry is also, there's something left to be understood. So for example, what exactly is this IH if I start with a matroid that is only representable over a finite characteristic field? So that's it for today, and we'll continue tomorrow from here.
Okay, thank you, Yoon, for a beautiful talk. And we have time for questions, comments.
I have a question about the last slide.
Mm-hmm.
Is anything known about how IH is generated as an H module?
That is very closely related to the coefficients of the Kazhdan-Lusztig polynomial. So I'm going to give you the precise relation tomorrow. So IH is not generated in general, not generated in degree 1. So this graded Möbius algebra is generated in degree 1. It's a graded algebra generated in degree 1, but the module IH is not generated in degree 1. So how many extra generators do you need in each degree? They turn out to be the coefficients of the Kazhdan-Lusztig polynomial. So at least you know that this IH is generated as an HL module by elements of at most d half degree, because the Kazhdan-Lusztig polynomials are required to have degree at most. Yeah. This is exactly the same phenomenon that you see in the cohomology and intersection cohomology of Schubert varieties, which is the source of the classical Kazhdan-Lusztig setting.
Thank you. Are there further questions, comments?
So maybe I have some more questions.
Yes.
And yeah, this is related to my the question I asked you before. So in order to apply the Hodge theory, you have to some algebraic variety for you to apply the Hodge theory, right?
Mm-hmm.
And it's I mean in the setting of his book, he uses the Kuma cover, right? Mm-hmm. Associate line arrangement to a certain algebraic surface, right? Mm-hmm. But how about in your case? You must also have some space to associate.
Yeah, that is the most fascinating part. So yeah, in my case, if you start with a matroid that is not representable over any field, in some precise sense, I can show that there is no algebraic variety defined over whatever field with such and such property. For example, having the cohomology ring as the HL that I'm defining. What I'm doing is I'm not applying Hodge theory. I'm proving what would be implied by the Hodge theory. So I'm brute force proving Hart-Lefschetz in a combinatorial setting. I'm brute force proving the Hodge-Riemann relations for this non-existent algebraic varieties. But
okay, I can. Yes, I can guess. Maybe you assume there's this line arrangement, for example, can be realized as a line arrangement in in complex plane or the complex projective space. Then you try to construct an associated variety. Then you get contradiction, something like this, using Hodge theory. Then to show this kind of arrangement, in fact, does not exist. It's the way you pull for your pull.
I think you're still thinking in terms of Hertzberg's setting.
Yes.
So our setting is very different, and it applies to all matroids, in particular all point configuration in whatever projective space, and possibly the ones that do not even live in projective space.
Okay. Okay. So yeah, I will try to understand. Okay. Thank you.
Any further questions or comments?
May I ask you one question?
Yeah.
Is there some, how can I say, a geometric way to understand your Möbius algebra?
So tomorrow I'm going to convince you that when my matroid is realizable over the complex numbers, then there is a complex cell projective algebraic variety whose cohomology is exactly the graded Möbius algebra.
Oh, I see.
So this is one of the few cases where a very singular projective variety has a very pleasant cohomology ring, where you can just write down how the multiplication works very explicitly. It's simply the join of subspaces.
I see. So for that case, it's a singular cohomology, right? Wow. Intersection.
Yeah, I mean, for example, if you start with a 4-point in general position, I have shown you that the dimensions are 1, 4, 6, 1. So you see the failure of the Poincare duality already in this case. But you know how to multiply in this cohomology ring.
I see.
What I'm doing is to produce a very pleasant module over this ring that fixes the failure of the Poincare duality. So there is a graded module whose dimension is 1661, which is module over the ring with 1641.
I see. Thank you.
So if there are no further questions or comments, I'd like to once again thank June for a lovely talk. I guess number 2 in this series will be tomorrow morning. The next talk this morning will be in about 25 minutes at 10:30. So thank all of you for tuning in, and hope to see you at 10:30.